Okay, so welcome everybody to the ECRYPT-NET Fellows Elevator Pitch Competition. So we're going to have the 14 fellows giving elevator pitch, talks, presentations of their research. And so the rules are they have up to 4 minutes, 4 slides to make a presentation describing their research that they've been doing.
You give us 60 seconds. I'm sorry, Carlos.
Yes. And so we have a panel of 5 experts. They're going to judge their presentations based on the criteria of the quality of presentation, the way they describe their research, and so on. And then at the end, we're going to have the top 3 with some prizes. And we have 14 presentations, so we're going to have a quick break after 7 presentations.
Okay, thank you. Well, if you have a test now, you really need to be careful now. 10 days ago, researchers from Cosecure 11 launched a near hack of Tesla Model S with a budget of only 600 euros. They can hack the Tesla Model S in only a few seconds. So the main problem of the Tesla is that it's protected by a cipher with only 40-bit key. That means it cannot, it's vulnerable to a classical 10 memory trade-off attack. Okay, maybe you don't have a fancy car like me, but however, nowadays it's really difficult to avoid using GSM, smart card, or TLS. So actually, world is suffer from weaknesses in the ciphers. So we see flaws in ciphers can be a big problem in reality. So our task is to evaluate the security of ciphers before deployment. Actually, in symmetric crypto, when we say a cipher is secure, we mean that all existing attacks cannot be more efficient than exhaustive case search attack. However, the thing that we cannot say anything about unknown attacks. So in my opinion, one of the main driving force for cryptography is to develop new evaluation methods to evaluate the ciphers. Like many existing ciphers, we develop new methods in a divide and conquer approach. Suppose that the keyless of the cipher is n. Our attack will be divided into 2 steps. In first step, we derive some Boolean equations of m bit and k bits, and then we can determine these m bits by exhaustive case search. Then, as the second step, we only need to make brute force attack against the remaining n-1 k bits. So in this sense, we have an attack with complexity less than exhaustive case search. So more technically speaking, we follow the framework of Q-attack, which has been proposed 10 years ago. By introducing a new property for the domain property, the classical Q-attack can be improved considerably. This enables us to find the weaknesses in the ciphers that we cannot find before. So additionally, we model the main attack stack with integer programming, integer linear program, which is a well-started problem. And we have many existing tools to solve it. So in conclusion, we have proposed new techniques for Q and modularly algorithmic attacks. And based on our attacks, we can mount new, we can improve results of parameters of many ciphers. Especially, we get new reports for analysis of many few ciphers. Such as Prevail, Acorn, and Trivial A, and C, and IC1 and IC2. And additionally, we developed an automated tool to implement our attack. This can be useful for future cipher designers. Our has been published in 2018, and the full version is on ECRYPT. That's it. Thank you.
Yeah, the title is slightly different, but hello everybody. Let's talk about the birds and bees, but for secured chips. Standard cell IC design flow is how the majority of digital circuits is made nowadays. It has been vetted by the EDA. This is not. So it has been vetted by the IC design industry for a number of decades, and it has been supported by many different EDA vendors. So now we have to on one end we can rely on this huge knowledge base to make chips. Right? This is what's known. But what's very new and fresh in this setting is the concept of side channel security, which is normally evaluated at the very end. And as a result of these only post-silicon measurements, a huge setbacks, or sometimes the need for the entire redesign can appear. So what people do when they don't mess up the ordering of the animations is either FPGA prototyping or formal verification as a design time methods to assure that the end results will be secure. What we are proposing is to actually be very closer to these decades of industry in the EDA and IC industry. We've been sort of working together to produce chips, and how can we leverage these methods to provide secure chips. So in the main challenges we sort of identified, or the requirements, were this trichotomy of, first of all, it has to be available very early in the design stages, so the designers can start this iterative approach and sort of just follow it along the way. Second of all, it has to be efficient in terms of computation and scalable in terms of circuit sizes, because otherwise, again, it's going to be useful. But most important, useless. Sorry. But most importantly, they need to provide very high confidence in or a higher level of assurance in the security of the end devices. So, as you could see, we sort of decided to deal with the entire stack of problems, and dealing along this stack of problems and the tools. So we wanted to sort of wrap everything together, and in order to practically implement all that, we designed this framework, which is very luckily abbreviated Cascade. It is the first open source framework of this type, and we've put a major effort to comply, first of all, with the EDA. So we are sort of easily integratable into designers' toolboxes. We support a high degree of automation, and also we rely on all these commercial tools and standardized data formats. On the other hand, we are also adhering to the standard cell ASIC design compliance. We're doing this iteratively in each step, and also we've done a lot of effort in optimizing this so designers can have real-time evaluations of their circuits. In terms of the third point and the confidence level that can only be achieved through multiple design iterations and multiple chips produced, and this is something that is ongoing at the moment. So thank you very much.
So hi guys. So I'm going to talk about privacy-preserving neural networks and how companies can overcome some sort of GDPR-induced anxiety. So in the business of machine learning as a service, we have a user, Alice, that has some private input, X, and she's talking to a company that runs on the cloud, and she wants some model that the company holds, some model M, to be evaluated on her private input X. So it's very easy. She can send X and recover M of X. Now let's see this from the point of view of an attacker, of some sort of hacker that wants to recover some private information about Alice. So there are several points that can be attacked in this model. So first of all, the hacker can try to hack directly into Alice's machine in order to extract X. He can try to attack the channel of communication, or he can try to attack directly the company's servers in order to extract private customers' information. So the company can say, okay, you know what, I'm going to encrypt everything. I'm going to encrypt all the customers' data, and then I will be fine. So I'm going to set up a key warehouse. I'm going to set up a storage facility, and then I will store all the customers' data in an encrypted form. Well, the problem is that this is not going to save the company, because first of all, it introduces more vulnerable points, And also, and more importantly, there is always a point in time where the customer's data travels unencrypted inside the company's servers, namely just before being evaluated through this model. So if we look at this shape here, we can define some sort of perimeter of liability for the company, because inside here we have private customers' data that have to be protected. Instead, our solution is different. So we first assume that Alice has not only her private input X, but also some private key, some golden key, that she will keep for herself. And now she will send an encryption under this golden key of the input X. And the company on the cloud, through some techniques that go under the name of homomorphic encryption, is going to be able to evaluate this model M directly on the ciphertext and send back an encryption under the same golden key of M of X. Of course, there can be a storage facility here, but everything that is going to be stored here is data which is encrypted directly by the user. So if we look at this from the attacker's perspective, he can still try to hack directly into Alice's machine in order to extract X or the golden key, but nothing else really, because apart from here, the data is always encrypted by the user. So if we look at this shape here now, this white shape, there is no sensitive data inside here. So there is no private input, there is no cryptographic key, nothing at all. So pros and cons of this solution. First of all, the company always processes encrypted data, which strongly mitigates the repercussions of a possible security breach in the company's servers. And also, the company is never involved into the encryption part, meaning that if something goes wrong there, it's really the customer's fault and the company will not be responsible for that. On the not so bright side, of course, it's hard to take advantage of the customer's data, meaning that they cannot be used, for example, for tailored advertisements, or that this data cannot be sold to third parties and cannot even be used, with some caveats, in order to improve the model itself. But of course, it's a trade-off between what you can see and use and what you're responsible for protecting. So if you can see nothing, then of course you have nothing to really protect and be responsible for. As for concrete results, this solution has been implemented, and speaking of neural networks, we can evaluate homomorphically neural networks at the speed of 16 milliseconds per neuron, with the possibility to massively parallelize the evaluation, for example, on a GPU. And also the solution scales nicely with the complexity of the network itself and opens the way to some sort of privacy-preserving deep learning that can be very interesting for companies that are in the machine learning as a service business. That's it. Thank you.
Oh, hello there. So you're also going to the ECRYPT-NET event. Well, this is the right elevator. It's just very slow, so I might as well use the time to talk about my topic, which is practical homomorphic encryption. So, okay, so you just came here to this resort to muse about the Holy Grail and to drink beers. Well, speaking about Holy Grails, my topic actually involves something called fully homomorphic encryption, and it is in fact sometimes referred to as the Holy Grail. And when I speak about practical parameters, making it practical, I mean devising a system, implementing it, and finding parameters within this triangle of correctness, because we're speaking about something called approximate homomorphisms, as well as security and efficiency trade-offs. So this is the domain I'm working in collaboration with Michele, for example, or with Pascal Payet and Florian Bourse. So we heard, you might have heard from the media that there is, of course, companies that are willing to host your machine learning algorithm for you. But I really want to shift the focus on the user side, because your data is valuable. Everyone wants your data, and you should protect it. So suppose you have some image that you would like to have classified by the cloud mechanism. Then of course you encrypt it before you send it. And then how does this look like? Well, more technical, we basically encode every pixel into a polynomial, and we send it over to the cloud where it deploys its artificial intelligence, magic I want to say, but it's not really magic, it's just mathematics, and it's very overrated. So what it actually happens is the scores after the homomorphic computations are sent back, and computing the argmax after decryption, you can actually find out what the label is that the artificial intelligence classified your data to. So let's look more about this magic, what's actually happening. So an image is typically a raster of gray values. So each pixel is represented by a gray value and is input in this first layer of this neural network, for example. Then there are several hidden layers. This is where the deep learning name comes from. And in the end, there is this output layer which classifies. However, the network never actually learns the values if they have been encrypted prior to sending them to the network. If you even zoom more in, for example, onto the hidden layer, we can see and inspect the neuron. What happens actually is a very well understood mathematical operation, which is just the inner product of the input vector x and of some weights that are encoded in the network. They are encoded because the network has been trained on user data before. And finally, there is some kind of activation. In our case, it's a really clamped sine function, and out comes a y. And in order to make this practical, I was speaking about practical parameters, we need to round and to make it all fit into same parameter space, and this needs to be carried on. But then, our network can be arbitrarily deep, and we showcased how, for example, to classify such an image with 96.3 or more accuracy in 1.6 seconds. So this is a fairly good result, and if you're interested, then please maybe go to the GitHub repository where we already have an implementation out there, ready to be deployed in GPU environment soon. And if it's not so interesting for you, then maybe go on musing about the Holy Grail and enjoy at the pool bar with a little beer. Thank you.
Hello everyone, so I'm Ralph and I'm doing my PhD at Walt Holloway in the analysis of lightweight and efficient symmetric key primitives. And yeah, you all know the Internet of Things. It's a network of embedded devices, vehicles, medical implants, home appliances, and so on. And yeah, practically speaking, security and privacy in IoT sucks. So there are many security relevant issues, there are some safety relevant issues, and also privacy relevant issues. For example, there was a huge botnet just out of IoT devices. Your smart fridge and your scale in your bathroom were kind of hacking, doing a big DDoS attack. There were some attacks on cars where attackers could directly overtake your whole car and drive you somewhere else, or just brake in the middle of the road. And yeah, for that, some dedicated lightweight designs were needed. So that's why we have lightweight crypto. And also speaking about what the money is in there, so there are about 30 million devices expected in 2020, and the global market value in 2020 should be about 7.1 trillion US dollars. So we can also phrase that, yeah, it's a very important problem. So what is our technical approach? Kenny told me yesterday it's not all about differential cryptanalysis. So what we did is also boomerang attacks, rectangle attacks, yo-yo attacks, zero correlation linear cryptanalysis, and integral attacks. And in symmetrically we don't use simulators, so we use advanced tools for automatic cryptanalysis. So what we implemented was some stuff with mixed integer linear programming. We used advanced SAT solvers and SMT-based solvers, and we implemented our own stuff in Python, C, and C++. And yeah, coming to my achievements for myself, so I got 4 papers in international conferences based mainly on cryptanalysis. I have one technical report on benchmarking ciphers, and currently 2 papers in submission. I also won the Skinny competition for cryptanalysis, and I'm currently holding some of the best attacks on several ciphers like Skinny, Sparks, Carmen, on this.
Right. Okay, so it's inevitable that as organizations store our personal data, eventually it's going to end up in the cloud. And as people become more privacy conscious and laws and regulations change to reflect our growing concerns for privacy and concerns over identity theft and so on, it's becoming the norm, I hope, that this outsourced data is encrypted. But it turns out that striking the right balance in security, usability, and efficiency of encrypted databases is really tricky. So my research looks at some of the implications of these trade-offs and how that can be interpreted. Specifically, I'm considering encrypted search schemes that support a fundamental type of query, which is range queries. This is usually for numeric data, but can be for other data as well. So rather than look at attacks on particular schemes, we consider attacks that work on classes of schemes with certain leakage profiles. So one such attack applies to any scheme whose query leakage includes the set of record identifiers matching a particular query. In other words, this is the access pattern. Another attack applies to any scheme whose range query leakage includes just the number of matching records, merely what we call the query volume. Our tool for the access pattern attack is a data structure called a PQ tree, which encodes a set of permutations. After every query, we can update this structure and thus group together records with the same value and eventually order them all. The output of this attack is a complete mapping from record identifier to value in that record. Now for volume attacks, what we achieve is something a bit less than for the access pattern attacks. What we get is the exact counts of all values in the database. And our tool for the volume attack is a set of, we first build a graph with a particular structure and then use a set of targeted heuristics to identify a click in this graph, which enables us to output the counts of the values in the database. The only previous generic attacks on schemes with such leakage profiles were specific to range queries that were uniformly distributed. So our attacks don't need this assumption at all. They work for pretty much any query distribution. Now, of course, to say how many range queries are necessary to be observed so that our attacks work, we have to consider a particular query distribution. So to compare them to the best previous attacks, if we suppose that the range query distribution is uniform, we require significantly fewer queries. Also, the access pattern attack can be modified so that you get partial results where you determine approximately the value of a certain record. And the volume attack can be extended once you've determined the counts of all values in the database. With just a bit more leakage, you can determine the value of a record that was newly inserted. By better understanding the implications of security, usability, efficiency trade-offs, we will, I hope, in the future make better informed decisions about which schemes are appropriate to use in practice. Thanks.
That 999 parties are conspiring against one. I don't believe so, at least. So what are the gains that you get in this case? What we do is that instead of each party having security parameter long keys, they're going to have some smaller keys. And of course, this gives you something that is insecure if you look at it individually. But now the security of this protocol is going to rely on the concatenation of all of these keys. And in particularly, this brings you to some very interesting problem that at least one person in the jury has been cryptanalyzing, which is this regular syndrome decoding problem from coding theory. So that's a very beautiful math behind it. Yeah, and what did we achieve? So if we compare in the constant round setting with the state of the art in 2015, our protocols are at least 3 orders of magnitude better in terms of communication, which is the bottleneck really here. So this is great. This is bringing us closer to this goal of having parties all around the world spread doing MPC. We also have understood better these functionalities, as I said, and this is something that people are really using. When people are referencing our work, they are building proofs based on our functionalities. So this is helping other people, which I really like also part of the analysis. And regarding the scenario having many parties, we have 2 papers, one in crypto this year and the other one is coming in ECRYPT this year. So the crypto one is looking at passive security. We improved the communication complexity of GMW, which is a non-constant round protocol by up to 25 times in the best scenarios. For constant round, which is this VMR protocol that I've been speaking on the other side, we improved by up to 7 times the size of the garbled circuit and the communication with garbling. And the online phase is up to 3 times faster. We have an implementation for that. Yeah, for what's coming in ECRYPT, we improved this TinyOT protocol, which, if you remember, is the one that's especially good for garbling. So maybe we can leverage this at some point. We reduce the communication complexity by up to 8 times. So that's it for me. Thank you very much.
Hi, so I'm glad Ralph somewhat introduced this topic for me. So there are 2 forces which are and will continue driving the idea of security that there is in the real world. So fact number 1, the number of connected IoT devices is exploding, as you can see from the graph, which is a prediction. And number 2, quantum computers will be a threat to our communication of tomorrow, but are already a menace to our forward secrecy of the present. So we, as cryptographers, are faced with 2 challenges. We have to, first of all, implement and optimize quantum resilient cryptography inside constrained devices that form the IoT ecosystem. And second of all, we have to also take care of the fact that once these algorithms are on the chip, they will start leaking, and side channel attacks will be possible. So I personally try to tackle both these challenges, and in particular I focused on the protocol Frodo. Frodo is a key encapsulation mechanism which is based on the security, on the hardness of the learning with error problems. The reason why Frodo is a somewhat peculiar choice in this area is that it's not based on usual functionalities like the number theoretic transform. It doesn't have a Gaussian sampler, and this means that many side channel attacks that are already present in the literature simply do not apply. And second of all, so Frodo is somewhat slower in terms of per cycle counts and performance on embedded device, so less attention has been paid to study it. So my contribution to the literature is threefold. First of all, I developed the first side channel attack against the implementation of Frodo software by leveraging only a single matrix multiplication. So matrix multiplication is the basic operation of Frodo, and imagine an adversary that can get the power trace or EM of one matrix multiplication. What they will find inside the power trace are chunks in which the same secret, here represented in red, is used with different publicly known values, which here are in shades of green. And those chunks will essentially represent multiple power traces that the adversaries can use to mount side channel attack. So I not only showed that this was possible, but it also only that this was possible, but it also achieves very good success rate in practice. A second direction I've been focusing on is to try and implement Frodo on an ARM Cortex-M4, which is a 32-bit microcontroller which is very IoT friendly, by leveraging several techniques, one of which, for instance, is the presence of SIMD instructions on this embedded device. So if you imagine that you have 2 registers, the top one storing 2 16-bit value and the bottom one storing 2 16 secret values, then with a single instruction it's possible to multiply and accumulate these 4 values together, so speeding up effectively the implementation of the multiplication. On top of that, we also use secret packing techniques, and our goal is to produce a very competitive implementation of Frodo, which, however, I can anticipate will leak like hell. So my also goal is to experiment and analyze different countermeasures that are present in the side channel literature, like masking schemes, shuffling algorithms, and plain text blinding. So to conclude, what I've achieved in these 3 years, I've analyzed Frodo and LWE-based schemes from a side channel perspective. I presented the first attack on a software implementation, which gave me many insights on how these things work when implemented. And I'm leveraging this knowledge to build a hopefully very competitive implementation of Frodo on an embedded device and to secure it for the IoT of the future. Thank you very much.
Also need to figure out how this works. I'm Dusan, and I'll talk to you about side channel and fault attack countermeasures in the lightweight setting. Okay. So, Ralph and Marco, they already explained to you about the wild west of IoT. But we're researchers, we want to bring some security to them still. But apparently cryptographic security is not enough. Because if you have physical access to the device, you can break it fairly easily. So analogy with a safe is, it's very hard to break the code. But if you listen to the lock mechanism or try to torch the door, you can get in. So if you have physical access to the device, you can observe the power traces or try to obstruct the execution of the device to derive the keys that you want to keep secret. So we need protection for this, but since this is IoT, it's a lightweight setting, so we have a lot of constraints with regards to power, energy, latency, and circuit size. So we have to work with this, so let's see what we can come up with. So first we studied what's currently there, and we find out that threshold implementations, or TI, are most suitable for hardware. And then we try to figure out how to improve on TI by finding suitable blocks for it, or by optimizing TI itself further. For fault attacks, it was a bit more difficult, because basically there was nothing there, so we had to build our solution from scratch. What we came up with is, so we managed to classify some new TI suitable building blocks, namely 5-bit quadratic permutations that are very easy to apply TI to. And we also made a constructive solution that provides the smallest TI, so with the smallest overhead, for complex functions of any number of input bits. And mainly, we propose a new theoretically sound side channel and fault attack resistance scheme based on applying another layer of masking on top of TI, a fine masking, that's resistant to 256 faults per execution, which is much better than usually 1 or 2, which was the previous state of art. Thank you.
Okay. Hi everyone. I know you'd all like to be at the beach, but not quite yet. But I'm going to talk about the seaside, such that you can at least dream of it for now. So what's the problem? I mean, what is seaside? It's, if you want to remember one thing from this presentation, it's essentially post-quantum Diffie-Hellman. So here's the problem. If you look at traditional Diffie-Hellman schemes, they use a group in one way or another, and it's essentially just based on exponentiation. So Alice and Bob both raise some publicly known value g to some power, and then they take each other's public key and do the same thing again, and they end up at the same shared secret. What's the issue with this? If you have a quantum computer, it's completely broken. There's no hope. Any group, even with the curse, which some people miraculously believe to be secure, it's just broken. And the problem here is that this algorithm makes a lot of use of this property that you can take two public keys and you have a meaningful operation on them, which is you just, well, if you write it multiplicatively, you just multiply them and you get something that has some algebraic relation to the public keys you started with. And this is the core property that Shor's algorithm makes use of. So one idea to still have a secure Diffie-Hellman scheme in a post-quantum setting would be to just get rid of this group structure and use something where you have less structure on this space of public keys. And this is essentially what we did. So to get an intuition for how this works, let's look at an example of how a normal Diffie-Hellman on a group would work. You have a bunch of nodes here, they're labeled by their group elements. And now let's say I want to compute g to the power of 13. One way to do this is I multiply. Of course, this is not going to give the honest user of the protocol an exponential advantage over an attacker, because we still have to iterate over all the intermediate values, so you can easily brute force it, so that's not secure. What do we do instead? Well, we square and multiply. And then we square again and multiply. And we square again. So the square multiply algorithm is in some sense the core of why Diffie-Hellman can possibly ever be secure. And if you think about this some more, it turns out that, well, multiplication by a fixed 2 power of g is just some kind of description of how to walk on this graph that has the powers of g as its node. And different powers of g give different graphs. So these are these different cycle structures. This would be g squared, and g to the 4th is this, and g to the 8th is this. And in some sense, square multiply is just a way of walking sort of randomly on the union of all these cycles. It's sort of constrained. I mean, you only walk almost once on each of these cycles, but it is one way of viewing this. And Seaside, our new scheme, is just this, except that the graph is constructed in a different way. But it is just union of a bunch of cycles, and then there's some description of walking left or right on one color of these cycles, and yeah, that's it. So this looks just like this. So I mean, I changed the picture a little bit, but it looks exactly the same if you think about it. And yeah, as I said, the nodes are now just elliptic curves, a certain group of elliptic curves, and the edges are certain kinds of maps between these curves, which are called isogenies. If you don't know what it is, don't worry, it's just lines. And so here's an example of what this looks like in practice. It's well, a certain kind of map. It's a bunch of polynomials divided by each other, math going on, but you don't really have to worry about it if you just want to know the big picture. So you can do it if you help by using this. It's just, well, on top there you can see the private key, it's pluses and minuses. Let's say go left or right, and the colors mark which of these cycles we're walking on. And now we can just have each of these parties compute their public key by doing this sort of random walk on that graph. And then they exchange their public keys. So we now just swap them. And they continue this walk using their private key again. And in the end, it turns out that they magically end up at the same value. Pretty cool, right? And what we did with this is, well, this kind of scheme existed already. It was introduced by Kovenia and independently later by Otsostev and Stolbunov, two Russians. But it used ordinary curves, which made it pretty slow because you had to have huge extension fields, and it was all kind of, it is super slow. And our contribution is essentially making this a lot tremendously faster by switching to super singular curves. The title of our paper is An Efficient Post-Quantum Commutative Group Action, which kind of hints that there's actually more than just this Diffie-Hellman scheme. It's just one nice application that we found, but there may be a lot more. Actually, somebody has found a signature scheme by now, which is not super fast, but it works. You can do it. And yeah, so this is a post-quantum non-interactive key exchange. It features efficient public key validation, which is not true for some schemes that have existed before, including all these lattice-based sort of Diffie-Hellman schemes where you have some noise. And it has pretty small public keys of 64 bytes, which is really small compared to the post-quantum schemes. And it's reasonably fast in the sense of, you know, a few tens of milliseconds. And we're currently working on making that even faster. Yeah, you can't see it, but it says thanks now, which means I'm done.
So please go ahead.
Thank you. So I'm going to present this scheme. That's a post-quantum scheme. We already know that quantum computers are bad, from Marco and Simon and Lawrence. And I really like this code because all the cryptography that asymmetric cryptography that we have, it's that. Also, it's because it's from my supervisor, so I really need to put some stuff for finish. So, and if you see, the problem is not just okay, we can broke the asymmetric crypto. The problem is, well, let's just store this, and we have this nice phrase from Orwell where who controls the past controls the future. So they can just wait and decrypt. Do we have a solution? Well, yes. As you could see from the other talks, we have post-quantum. But in our case, we have key encapsulation from the attic generalized Istravastava codes. That's what short for DAX. It is a McAllis variant. We have small public key, comparable for other submissions in code-based, like really small. Small ciphertext. And if you are in the list of NIST, 2 days ago, 3 days ago, they just released this power efficiency. And surprise, we are the ones that use less power for encapsulation and decapsulation. Also, I would like to say that we are patent-free. So, who doesn't know, some of the schemes, they have patents on top. And yeah. But let's see how we do this. What's the math behind this? As I said, we use generalized Stravastava codes and use the attic matrix. Operations in finite fields 2 to the 8 and 2 to the 16. Here we have an amazing matrix that we use. And in theory, it's so beautiful, it's perfect. But let's try to implement inversions in a computer, and the things are starting getting really nasty and slow. Or, well, at least in our case, it's slow. But good is that we could improve this. if you just take all the inversions on DAGs, that was the count cycles. And after we just improve some things using like Ratsub and LUP decomposition, we could speed maybe a little bit especially our key generation. So that's like, now it's something, as Lohan said, competitive performance. And I think that is all. Thank you.